Hi, welcome back to the lecture series on GPU architectures and programming. So, coming to the continuation of the earlier lecture, I believe we have been talking about multi-device programming. We have built a context containing multiple devices. We have set of queues, multiple command queues, each one queue for one of the device, and we are trying to see how the devices can execute kernels concurrently. So, in that way, this was our example that I have got this program through which we are setting up two queues, one for the CPU and one for the GPU, and we are trying to have this kind of a behavior that the kernel running on the GPU device has got some output. The kernel running in the GPU device has got some output, and that output is going to be used by the kernel running on the CPU device, right? So, just a small change here, like as per this model, what we have done is the CPU is device 0, GPU is device 1. I believe that has got exchanged. So, I hope that can be figured out anyway. So, coming to the problem further. So, suppose we want this execution that you enqueue first in the GPU. So, let us say we call device 0 as GPU here, although it is a bit different here, device 0 is CPU, but let us go with the figure here. I believe the concept would be clear. So, for device 0, that is the GPU, you want to enqueue the kernel. So, this is how you will do it. You enqueue the kernel, but what you do is along with that you have a declared events, event 0 CPU, event 1 GPU, and maybe I believe we'll just say we'll just say these are events GPU and event CPU. So, this event CPU and event GPU. So, when this kernel executes, it will just output an event GPU, and all you want is the second kernel should start only when the event GPU is available to it. So, it is sensitive to event GPU. That is why for the CL NQ range kernel, you are enqueuing this kernel at the point, I mean you have enqueued this kernel into the CPU queue, CPU, and for this kernel you are waiting for the GPU kernel to finish. So, when the GPU kernel finishes, it outputs the event GPU event. So, since I have it in the event list, I make this command sensitive to event GPU. So, when this is received, I will have the other kernel which is enqueued in the CPU queue. This will start executing, and when this finishes, it will emit this event CPU. Now then we have these two CL flush commands like discussed earlier to flush both of the queues, and this only guarantees that all queued commands to the command queues, they will eventually be submitted to the appropriate device, and but of course there is no guarantee that they will complete after the CL flush returns, right. So, this is something we have already discussed, that if I reach, these are all in asynchronous commands. Such commands are getting enqueued here in the host program, like this is the host program, I am using it to enqueue the commands. But once these commands are enqueued, when I do a CL flush of each of the queues, the CL flush is assuring that whatever commands I have enqueued for the CPU, whatever commands I have enqueued for the GPU, they are dispatched to the devices. Whether they are finished or not, that I am not ensuring, for I will have to put in something else like CL finish. So, this is just a demonstrative code to give you the idea that what is the utility here. So, please mark this correction, and also here just like we had device 0 and device 1 for the CPU and the GPU, and this is a bit different. So, that will be another here. Now, without going into the detail, let's say that how I can make it more generic. For example, I want multiple devices programming working concurrently, and I have more number of devices. Let us say I have got 3 devices now, and I have multiple devices working in a parallel manner, and both of these GPUs do not use the same buffer, and they will execute independently, and the CPU queue shall wait until both the GPU devices finish, right. So, let us say that is what I want to happen. So, maybe for the idea is that kernel 1 will execute, kernel 0 will execute in device 0, it will output something in the memory buffer, then kernel, and in parallel kernel, so kernel 0 is executing in device 0, that is the command queue of one GPU. Kernel 1 is executing in some other device, which is device 1, which is the command queue of another GPU. So, as you can see that they are independent kernels, they can execute in parallel, and after they have executed, let us say that they copy the data to the memory buffer, and then the requirement is I have a kernel 2 which is supposed to execute in device 2 here, which is a CPU device, and I have enqueued this execution command here in the command queue of this CPU device with the dependency that this kernel should wait and it should start executing when the kernel 0 and kernel 1 both of them have completed their execution. They will then access them, and then they will output the result. So, we are trying to see that how that can be done. So, overall, in a summary, this is an implementation example of a concurrent and pipeline model of multi-device execution, where I have a single context on the platform, but with 2 GPUs and 1 CPU device. So, what we are doing is we are creating 3 command queues, 2 queues for the 2 GPUs and 1 queue for the CPU. The kernels are enqueued on the CPU command queue. They wait for the kernels which enqueued on the 2 GPU command queues to finish, and when both the GPU devices have executed concurrently and they have their and they have done their job, then only I want the CPU kernel to execute. But these 2 GPU kernels, they have no input dependencies, so they can just go on executing without any event for which they have to wait. So, they do not have any wait list, right. So, since they do not have any wait list, I can have these queues, Q for GPU 0 and Q for GPU 1. I can just immediately enqueue the kernels. I do not have any wait list, so the event wait list is null for both of them. But when this one is done, this kernels are done for GPU 0 and GPU 1. They will be emitting the events, event GPU 0 and event GPU 1. Now, the functionality I want to implement is that the CPU should enqueue a kernel in its queue CPU, and this kernel should wait for both of these events, right. So, that is captured by this event list, right. So, I have event GPU, this is the event list containing 2 of these fields. So, only when both these events go to their complete status, then this kernel which have been queued here can start executing. So, kernel CPU can only start executing after kernel GPU in both the devices have executed, and this dependency can be captured like this. I do not want any more dependency, like there is no further execution based on the completion of the execution of kernel CPU. So, I do not have any further dependency, this is set as null, and like earlier we can just flush all the queues. That means these commands are ensuring that all the previous commands from each of these queues have been dispatched. So, this is something I will keep on saying. This is again a host program, it is just queuing the kernels for execution, it is not forcing them to execute, and the queuing is done along with dependencies. So, when the program reaches here, I will wait here until I ensure, because this is a CL flash, this is a synchronization primitive, the host program will go past this only when it is ensured that GPU 0, this queue, the kernel that has been enqueued here, that has been dispatched. So, that is ensured, then I will wait in CL flash queue GPU 1 unless and until the kernel that was enqueued here, that has been dispatched, and finally I will wait here and I will get past this point only when this kernel, which is kernel CPU, which is waiting here, that gets dispatched. That means it has to ensure that the previous kernel has finished and the events are fired, so that this can start executing, right. So, in this way the CL flush is actually forcing the execution to happen, and because otherwise the host program cannot go beyond this point, right. So, with that we have our discussion on multiple device programming with multiple command queue support for a same context. Now, let us talk about a scenario where I have multiple command queues with different contexts in different devices. So, the typical scenario you will want to do is you have context created with respect to particular platforms, and in different platforms you have different devices, like that hypothetical example we were trying to demonstrate earlier. In each of these contexts you have different devices, and for the different devices you can create separate contexts, and you can synchronize. And since you have now devices sitting in different contexts, you cannot synchronize execution of events across contexts. That is not possible. So, in that case you have to go through the host program. So, the only way to share data between devices would be to use CL finish, because if you have CL finish, then those command queues have to actually I can go beyond this CL finish synchronization primitive only when all the commands that I have enqueued so on up to that point of time in that queue, all of them commit and finish their execution. Then once that is done, I have the output data of that execution in that device available. I have to explicitly copy it from one context to the other context, and then inside that context I can start enqueuing commands for using that data in this separate context, right. So, in this way the idea would be that I have to orchestrate of data movement across contexts, and I have to use primitives like CL finish to ensure that execution has actually finished in one of the contexts, so that the data is ready, which can be moved across to a different context. So, if we look at such examples, that you are creating multiple command queues with different contexts that are sitting in different devices. You have different contexts sitting in different devices, and you are creating different set of multiple queues for the devices. In this example, as you can see, the typical code would be like you get the platform IDs like earlier, and then of course you should have a context array, and you have a set of queues, right, CL command queue array for each of the platforms. So, as you can see, you have a context array and you have a command queue array. So, you have context array for per platform, right, and you can also have this command queue array as we discussed. And the first thing you will do is you will try to discover the set of platforms, right, from and their platform IDs, and then once you have got the platform IDs, you are trying to get the device IDs. So, this is the kind of code we are a bit familiar with. So, inside the loop you are looping inside the number of platforms. For each platform you get inside the loop, you identify all the devices in the platform using this command. As you can see that if you are using CL get device IDs with the flag CL device type all, is discovering all the IDs, all the devices, total number of devices, and that is pushed into this num device variable, and then you you allocate suitable amount of memory, which is equal to the number of devices multiplied by the size of CL device ID. You allocate that much variable to this device IDs array, and then again you give a call to CL get device IDs, so that for this specific platform we are inside a loop. In each iteration we are inside one platform. So, for that platform all the devices IDs that have been discovered, they are actually provided into this device ID array, right. Now, for all of these devices together, what you can do is you run this kind of a loop. Using this loop you are creating a set of contexts, separate context for each device, as you can see. So, technically what we are doing is we have a set of platforms. For each platform you discover the set of devices. For each device whose ID is stored in this device IDs, and this is done in the last line. For each device you store its IDs in the device IDs array. For each of the device IDs you create one context. For each of the device IDs, inside each context you create a command queue, right. So, this is how you move forward. So, this is an example program. We are trying to show examples of pipelined execution of multiple kernels in different command queues in this case. So what we have done is we have defined two contexts for two devices, and each of these devices have their own command queue. So let's say this is one platform, one of the platforms. Inside this platform I have two devices, D1, D2. For each of these devices I have created a context, or better to say, and for each of these I have inside each of these contexts these devices and their command queues, right. So I would say I have a Q1 and I have a Q2. This is the kind of setup we are looking at. So now consider that I want to execute things in such a way that there is a dependency between kernel 1 and kernel 2, that is the output of kernel 1 is used as input to kernel 2. What we do is we have a CPU and a GPU in the platform, and I assign kernel 1 to the CPU and I assign kernel 2 to the GPU, right. So for doing this, whatever code is required, let's say that has been already written here, and in that way, and I have set up both of these queues. One is the queue for the CPU, which is one of the devices, one is the queue for the GPU, which is the other device, and they have been assigned the task of executing kernel 1 and kernel 2. So first I do a write buffer. So in the queue of CPU I do a write of some buffer A, and then in the queue of the CPU I do a write of the other buffer B, and then I execute kernel 1 in the CPU, which will be working on the data of buffer A and buffer B, and once it is done, it will output this kernel event. Okay. Now I have this read buffer command here, so that's a way I can ensure that well, this has this command which I enqueued for launching a kernel, which is kernel launch, that has been finished when this kernel event shall fire, and this is in the event list for read buffer. So only when this kernel has been actually launched from the queue to the device, the CPU device, and it has finished the execution, I will have this event ready, and with this event firing, now I have the read buffer command ready to execute, and with that read buffer I will have the buffer C, which is the output of kernel 1. It will be transferred from the it will be transferred, and once it is transferred I will have the read event this read event set, right. And at the end I have this CL finish here. If I go the host program goes beyond this point, that means all these commands that I have queued up in the CPU queue, they are actually dispatched even though they have not finished their execution. So here I am blocking it until all previously queued commands, sorry, this is CL finish, it's not CL flush. So I am actually blocked here until and unless all these commands which have been queued up, they have been dispatched as well as all of them finish, right, because this is CL finish, this is not a CL flush. So they have finished execution in the associated device. So all that is happening is almost same. Only thing is here we are showing that we are working with different contexts, right. We have this kernel data which is there in different contexts. I mean, since they are in different contexts, so I have to make these reads and writes. So I put the data in the context of the CPU, right, and then so for that I have to enqueue comments, and then I execute the kernel. After executing the kernel, I have to read it back because it's not in the the GPU device is not in the context, and then I have to read back the data from I have to read back this data to the context of the GPU. So for that I will now again have this write buffer command executing. So it will copy some buffer D to the queue of the GPU, and then I will have kernel 2 executing in the GPU. So, as you can see that this is going to execute only when so I have this kernel 2 which is executing here. Now, for this I have a guarantee that since I have put in a CL finish, so all these operations that were done earlier, they have finished. So, after that I have this kernel 2 executing, and once I have kernel 2 completed, which is being ensured by the event kernel event, which is there in the sensitivity list of this command for this read buffer command. So only when kernel event fires, that means this is done, then only I am going to read back the output. Assume that it's there in some buffer out, I am going to read it back, and then I give again I fire the read event command. So again I will put in a CL finish in the QGPU. So I have this two contexts for the two devices. Each of them have their own command queues, and there is no dependency between the two kernels, and they can execute completely concurrently. So if I want that kind of a behavior, then I would just enqueue them in parallel without any kind of dependency. Coming back here, so if I have this line of the code, the execution is pipeline. That means kernel which is executing in the CPU, once it is done, so this is how the kernel is executing in the CPU. The read commands have been, the write commands actually ensure that buffer A and buffer B are copied in the context of the CPU, and then the kernel executes in the CPU, and then the output of the kernel, which is buffer C, is copied from the context of the CPU to the host side and then once I have copied this, so these are the host side data points. Maybe we are not showing how they are initialized. Assume that HA, HB or HC are available in the host side memory. They have been declared malloc. HA and HB has been initialized. So we copy the content of HA and HB into buffer A and buffer B, which are in the context of the CPU device, execute the kernel, and then after the kernel executes, I have the data available. So I have a read buffer now, which is ensuring that the kernel is executed through this event dependency of kernel event, and then it reads back. So and it reads back the content of buffer C to the host side memory HC, and then this is being written to the there is a write buffer command which is writing HC in some buffer D, which is there in the context of the GPU. So maybe if we just repeat what things are going on. So I have these two contexts there, they are separate contexts. That is why we are doing all these reads and writes. So you have CPU, you have the queue for that, we have enqueuing commands, you have the GPU, you have just put them in separate contexts, right? And we are trying to see that since they are in separate contexts, I have to set up the buffers, the buffer A and B, where I copy the data from the host side H underscore A and H underscore B. The kernel will execute, it will have the data in the buffer C. From that I will copy back to HC, the host side memory. Then I will be copying HC to the GPU side buffer D, and now I will have this ND range kernel GPU which is going to start execution, and once it has executed, you will see that it will output again another kernel event. Okay, so it will again output an kernel event here, and this kernel event is actually being used for ensuring that now when to start that I will do the read buffer again. So this the output is available here in some buffer out. The output of this kernel 2 is available in some buffer out, and then it is copied back to the host side memory, which is H out, right. So, this is how things are happening, and finally, we will have a CL finish to flush out both this queue and the other queue here. So, this is how we are trying to show that how things are pipelined. That means when the execution is done, we are able to actually copy things to the next device. Of course, when and how this is useful, that's something that you have to figure out where this is at all useful for your application. We are just trying to show that how things can be done, that how you can have device executing in one context and you can get the output from that context and you can copy it to the other context. We are trying to show that it is necessary when you have devices sitting in different contexts, then the memory objects are not shared. So, whatever is the output of a kernel executing inside one context, it needs to be copied to the host side memory and it has to be copied back to the other context. Okay. Now, of course, if there are no dependencies here, you can just enqueue stuff in two different contexts, queues in two different contexts, and they can just continue execution, right. So, overall, if we are talking about such concurrent kernel execution, so then this concurrency is a property of a system in which you have a set of tasks and they can remain active and make progress at the same time. The programmer would need to identify the concurrency in their problem in case you want to develop a program for such concurrent execution in a heterogeneous platform, and the point is it's the programmer's job to remember the differences, the abstractions, and accordingly do the mapping of the workloads or the kernels and their dependencies into different devices through the abstraction of device, kernel, and platforms. And also the programmer has to use this idea of events and their synchronizations to efficiently schedule the host program. And the concurrent tasks that may be running will be of the following kind. You can have different kernels for different independent applications. You can have different kernels without any kind of dependency between them. They are from the same application. That is also possible, right? To have two independent kernels running. Maybe on both of their output something else can depend, but these two kernels have no dependency. That is also possible. So, this is also when you can have concurrency of tasks or kernels, and you can have the situation that you have one kernel, it has been partitioned. Let's say the kernel requires 1024 threads to execute. You just partition the input data space to two different devices. You copy it in a partitioned way to two different devices, and you launch half of the number of threads into device 1, half of the number of threads into the device 2, and execute them. So, that is also a partitioned instance of the same kernel, and this is also like concurrent task execution. So, these are the possibilities in which you have concurrent task execution in a multi-device platform. With this, we like to end this lecture. Thank you.